Hi again, everyone. So this is the first of I don't know how many segments for Chapter 5, Section 2. I'm getting a little bit more adept at the use of this particular technology, so I think that we're going to see a lot of consistency here in very quickly. So the learning curve is kind of steep, but I think we might have hit a plateau at this point. Okay, so without any further ado, I'm going to transfer over to my document camera. And while I'm doing that, I'm going to make a couple statements about what we have in section 5.2. So section 5.2, just like before, I'm going to keep a running total of pages, and I will upload those pages when we're all said and done. Okay, so basically 5.2 is where we really start the mechanics of proving various trigonometric identities. Now, in general, at least for section 5.2, they all use the so-called fundamental identities that we talked about in section 5.1. So what I'm going to do first here, and we're going to see how far we get with this segment. Like I said, I like to try to keep them under 20 minutes or so. So we'll see where we're at. 5.2 is quite a bit longer than 5.1, so I'm suspecting this may be 4 or even 5 sessions. Anyways, so one of the first things and the key to really being proficient at doing trigonometric identities is that, let me just maybe call this strategies or techniques. The very first one, and this is so critical, which is why we kind of went over from the beginning, is that you must have a command of the fundamental identities. Without being able to rattle them off, you simply can't make use of them, and that's really sort of critical. I mean, in much of trigonometry is a bunch of memorization. We've already memorized, specific values for trigonometric functions of certain angles, like sine of 30 degrees or whatnot. But here we're starting to get into some things that are a little more challenging. We haven't been exposed to them, but you really quite simply must be able to memorize these, and you must know which category they come from to be truly successful in any of these proof techniques. So that would be, I would say, sort of number one. Now remember, what are the fundamental identities? I'll just write down their categories. We have the so-called reciprocal IDs, and there are 6 of them, right? We have the quotient IDs. Remember, there are also 6 of them, but it's like, an equals, or sorry, equals. So that there's one for tangent, has 2 different expressions, one for cotangent. After the quotient identities, we have the Pythagorean IDs, and there are 3 of them, right? Then we have the so-called cofunction IDs. I believe that there's 6 of those. And then the final set of fundamental identities that we talked about were the so-called symmetry identities, which are where you have negative signs in arguments. And there are 6 of those as well. Okay, so these are, it is critical to have all of these at your command. And you will use these for the rest of your life, to be perfectly frank. If you're going to go into any kind of science or mathematic fields, technology, having these available is critical. The analogy might be, you might know, if you know how to add or subtract, then why do you need to know how to multiply? Well, the fact of the matter is multiplication makes you more proficient at arithmetic. Knowing these identities makes you more proficient in anything involving trigonometric functions, which is basically anything that has more than one dimension to it, which is unfortunately, is the universe we live in. So that's sort of the first step. You must have a command. You must have a command. Have a command of the fundamental identities, and they're listed for you. Okay. So the second sort of advice, and this has more to do with proof technique. So when you have a typical show that sort of problem or prove that a certain statement is true, you have sort of statement on the left, usually an expression of some kind, and in this situation, it's always going to be some sort of combination of trigonometric functions equal to statement on the right. Okay, and your task is to not to use the fact that these are equal, but to show that they must be equal. Okay, and in order, from a logic standpoint, you can't assume that two things are equal and then show that they're equal. You haven't really done anything. And what I see when I'm analyzing students' proof techniques is that it's very, very common for students to do that, where they just simply, start with what they're trying to prove, and then lo and behold, they manage to prove that it must be true, which is just doesn't really contribute anything, and is logically false. It is not really a proof. So what's the strategy? Okay, most of the proofs we will do, you're going to start with one side or the other, okay? And maybe to label them, I'll just go ahead and say A and B, all right? It's not universally true, and of course there are much more complex proof techniques, but I believe everything that we do in this class are direct proofs. We're not trying to assume that, say A is not true and then other kinds of techniques like that. But basically, we're going to string together a series of equal signs. So how this typically works is you select one side of the equal sign, and there's some talk about, and I'll discuss which side to pick in many cases. So you start with, say, side A, and through some fundamental identity or another known identity, you'll show that a statement, say A1, is true, right? So this has a rationale, right? And then you'll have a next statement. Again, some kind of rationale. And this may continue until you end up with, hopefully, statement B. This is, and again, that may have a rationale as well. This is a standard sort of direct proof. You start by assuming that the left-hand side is a true statement, and then using only a priori known true statements, that is to say, identities that you're already aware of, you prove that A1 A is equal to A1, then A1 is equal to A2, then ... finally ending with B. And this is a successful proof. Usually the shorthand is to put a small square box when you've completed the argument. So you'll see me do that when I do these proofs as well. Okay, so that's advice number 2. Now, the question that comes up is, it's like, well, which side should I start with? And the statement that I usually make is, start with the more complicated side, whatever that means. I think that in many in many instances, you'll be able to tell which one's the more complicated. Start with the more complicated side. So if B happened to be more complicated than A, you may actually start with B equal to, say, statement B1, B2, and end with A. It's perfectly okay to go from left to right or right to left. And there's even more complicated situations that we come up with later as we move along. So the question then is, maybe just I could say real briefly, what is a more complicated side? What does that mean? Well, typically the way that I interpret a more complicated side is to think about how many algebraic operations are involved on any individual side. Division is more complicated than multiplication. Subtraction is more complicated than addition. Multiplication is more complicated than addition or subtraction, right? So if you have a bunch of fractions on one side or ratios of different trigonometric functions, if you have a bunch of parentheses, if you have multiple trig functions, or if you have trig functions that you're less familiar with, all of those sort of items come into the thinking of what it means to be a more complicated side. But I'll talk about that as I actually do some proofs, which probably will be in the next video segment. Okay, so moving on then. Page 2 here. All right, so the third piece of advice is that, and this isn't universally true, but sometimes what ends up happening is people get a little stuck, right? You don't really know how to move from where you're at to where you're going. Usually, the techniques that we developed at the end of section 5.1 can give you a little bit of insight. It's not always universally the case, but sometimes it is helpful to transform an expression into sines and cosines only. And you may recall that that was an exercise that we talked about in, I believe, the third segment of the videos on section 5.1. There isn't much really to say about this. It's just it's kind of a strategy that you can try to employ, and sometimes it makes things look a little more clear how to get from point A to point B. Also, I want you to remember many of the problems we have can be simplified by either foiling something out or factoring. So algebraic factoring is pretty critical. So algebraic factoring is still important. And I'm just going to remind you of a couple sort of very important algebraic factors. So here's an example. If you had, and usually if I was in a classroom, I would ask people to do this because it turns out for students of algebra, when they start a college algebra class, roughly about 70% of students will make a mistake when they do this factorization. By the end of a college algebra, it's really maybe like 40%, but it is very, very common for people to make these sorts of mistakes. So recall, if I had some expression plus or minus some other expression, and it is squared, that this is equal to a squared plus or minus 2a times b plus b squared. Now remember, with factoring, you usually have this, and you want to turn it into that, right? That's why that's a harder process. Going from a factored form to this sort of an expression is what we mean when we say, quote, FOIL it out, right? Just simply perform the operation. It's also called distributing, right? Distributing. But this is the hard part, right? Being able to see these collection of terms, which may not be in this order even. They could be all kinds of goofed up, and say, oh, hey, that's a perfect square, right? So that's an important important factoring. Now you'll see other kinds of trinomial factoring and everything else, but I'm going to focus on kind of the weird ones just as a quick reminder. So I don't know if y'all remember this difference of cubes. This happens to have sort of an interesting form where it's a minus b. Notice the minus sign is the same, and then it's times a squared plus ab plus b squared. Notice that the shift in sign occurs right here. And if I'm just going to go ahead and do a sum of cubes, so you can see what I'm talking about. So for the sum of cubes, it's actually a plus b. The SIGN is the same. And then the second factor, actually, that's where you see the change in sign, where it's negative as opposed to positive. Just compare those a second. Okay, we will not do a lot of that, but that's something to always be looking for. If you see a trigonometric function that's raised to the third power, it might be a good idea to see if you can possibly factor it in some way. Or, anyways, so another kind of important factoring classification is what's called the so-called difference of squares. And you hopefully, like, I mean, I know it's kind of weird when you've got A and B there, but this is the kind of thing where it leads to, you know, the use of the conjugate and every other sort of thing along those lines. But remember, the factorization of a difference in squares is the first term plus the second term times the first term minus the second term. And you can verify, if you FOIL this out, you'll end up with what's on the left. The cross term will actually cancel out. The O and the I have an opposite sign, so they disappear. Okay, so what else we got? We've got quite a few more sort of strategies here, so I'll just try to keep plugging along. Strategy number 5. And this is maybe just a statement. As you work through a problem, you want to remember to look at the target expression. So what does that mean? It means that if you started on the left-hand side and say that left-hand side has, I don't know, like sines and tangents in it. And the right-hand side has a cotangent and secant. Well, you have to remember that you have to do something with the left-hand side, assuming that's where you start from, that gets you these other trigonometric functions. So you're going to be looking to use fundamental identities that relate what you have to where you're going, right? And I can't really say it much more simplistically than that. You know, just remember to look at the target expression, and maybe I could say, and use appropriate fundamental identities. When I say appropriate, I mean things that have what you're looking for. Okay, I'll hold that there for just a second. Moving on to the next set here. Okay, so that was the 5th suggestion. 6. This is really more of a statement of what the expectation is in terms of a good proof. You need to provide a rationale or justification for each step, okay? And that's where a lot of students just don't do this. They know that, oh, I don't know, that cosine is the reciprocal of secant, and so they just write that somewhere, and then they write half a dozen other sorts of transformations, and it's not clear to me as the assessor, as the grader, whether or not the student actually knows what they're doing, because sometimes it can just, you know, you can get, all of these statements are true, you know, all of these proofs, when you're being asked to show that something is true, you know that it is true. In my experience in graduate school, the worst kind of problems were where you didn't know if they were true or not, and you were asked to prove or disprove. Well, you don't have that problem. You're always going to know they're true, and so you can fall into the trap of making stuff up that just simply is not true. So if you keep this in your head that I need to provide a rationale or a justification for each step in the proof, then you'll avoid just writing down nonsense. Okay, that's just, and I've seen enough nonsense that believe me, it has no bounds. Okay, so the suggestion number 7 is to recall or remember you can always multiply an expression by the number 1. Okay? Now that sounds like really dumb advice, but I want to point something out. This 1 plus sine of x over 1 plus sine of x, that equals 1, right? That is equal to the number 1. And so if I had an expression that for some reason multiplying by this product, like say, for example, 1 plus sine of x over 1 minus sine of x, that might make sense to do this exact multiplication, because what I end up with in the denominator here, notice this is a plus b times a minus b, is going to be, and I'll leave the top alone, but you'll have down here 1 minus sine squared of x. And that's critical because 1 minus sine squared of x happens to be equal to cosine squared of x. This is a very, very common technique. It doesn't have a formal name, but what I have called this is a trigonometric conjugate. Right? You have, here's one of the conjugate pairs, here's the other. You do this kind of thing all the time in these proofs, and I'll show you those as they come up. So finally, and this is probably the best advice, period. The only way that you are ever going to get good at these is by practicing. You can watch other people do them. You can watch your friends do them. You can watch YouTube videos of them, but until you do it yourself, you will not develop the skill that is necessary to be able to be proficient at proving identities of any kind. There is no substitute for hands-on. Okay, so I've gone probably a little bit longer than I wanted to here. I will be back again with segment 2.